Hi and welcome to this video where we're going to look at some trigonometry exam questions. This video is very useful to use in conjunction with our trigonometry review. The video for this is linked in the description below. Example 3.1, using the formulae. The diagram below shows a triangular patch of ground, triangle SGH. SH is 58 meters, which is given on the diagram. GH is 30 meters given on the diagram, and angle GHS measures 68 degrees, again given on the diagram. The circle is a helipad and it is the incircle of triangle SGH and it has its center at P. So we have our incircle. Find the length of SG and give your answer in meters, correct one decimal place. So forgetting about everything else, we have a non-right angled triangle that has two sides and the angle in between. So what we're going to do is we're going to use our cosine rule. So the first thing I'm going to do is I'm going to label it. So this is angle A and the opposite side is A. I'm going to call this angle B and the opposite side is B, and this angle C and the opposite side is C. So our formula, which is given on page 16 of the log tables, is up here. So we're going to have A squared equals B squared, so that's 58 squared, plus 30 squared minus 2 BC cos of 68 degrees. Now just double check before you do anything that your calculator is in degree mode. So degree mode. So if you're using a Casio, it should have a D up the top. If you are using Sharp, it will say DEG. If it doesn't, change it now. We'll put that straight into the calculator because we can. And we get A squared is 2960.369. And then to get A, we'll do the square root, and we're going to round this to one decimal place, which is 54.4 meters, and that is the length of SG. It's a very straightforward question. Part B, find the angle HSG. So we've just worked out that this side here is 54.4 meters. Labeling that again, we said that that was A. We said that this is B and that was C. So this time we're going to use the sine rule. We're looking for the angle HSG. So we're looking for angle C. So we have to use A. So we're going to use A over sine of A. And we're going to say that that equals C over sine of C. Now we want the angle, so actually what we can do at this point is actually use the reciprocals of this formula. That means flipping both fractions. So that's the same as saying, well, the sine of A divided by A will be equal to the sine of C divided by C. The reason we do that is because we actually want that angle C. That means it's in the top of the fraction and it makes our algebra that little bit easier. So 54.4 is equal to the sine of, I'm going to call that still angle C, all over C, which is 30. Multiplying both sides by 30, we get sine of C is equal to 30 times sine of 68 all over 54.4. To work out the angle, we're going to do sine inverse. So I will leave this to the very last minute to do any kind of actual calculation. That means I'm not wasting my time writing in decimals, which can be done incorrectly. Now some people would prefer to have decimals rather than what I have here. That's absolutely fine, but this is going to be the most accurate. We want this correct to two decimal places. So when we put this into the calculator, we're going to get 30.75 degrees. So that happens up here, that we have 30.75 degrees. So the next thing they ask us to do is to find the area of SGH. So we have an area formula on page 16 as well, and that's a half AB sine C. So I'm going to relabel, so I'm going to change my labels. You can do this in a different color. So I want the angle to be C. And you can use anything, like we have two different angles. I prefer to work, if possible, with the things and the information that they give us, because that way it is definitely accurate. So this is going to be a half A B sine C. Now, if you worked the other way, you should get the same answer. If you are rounding it like we've done, there may be one decimal place out, but it's not going to impact the question. So when you put this into your calculator, you get 806.65 meters squared. So really, what we're focusing on here for this area is a half AB sine C. That means half of two sides and the angle in between. So we do know C, and we do know the angle A as well. So you could use those. You could work out the angle at B because all the angles add up to 180. I am literally using the information that they gave us, and now I know for sure it's 100% accurate. It does mean relabeling, but there's no problem relabeling if you have a few different colors or even using a highlighter. So part D, find the area of HSP in terms of OR, where OR is the radius. So what we're going to do is I'm going to just put in those missing lines here. So it is HSP. So this line comes down here. So that's the triangle we're working with. We don't have any angles there, but we can use our traditional formula, which is half the base, which is 58, by the perpendicular height, which is OR. We know that this is perpendicular because it's the incircle. And when we have an incircle, the sides of the triangle are tangents to the circle. So that is times OR. So that works out as 29 OR meters squared. So show that the area of the whole big triangle in terms of OR can be written as 71.2 OR. So we've already just got one part of this. So what we're going to do is we're actually going to break the triangle into three little triangles. When you do that, each one has a perpendicular height of OR. So here as well. So I'm going to use a little bit of highlighter to help on this. So we have this triangle here. So there's one that we have. We then have this triangle here. So that's the second. And the third triangle we've actually already worked out. So that's the one in OR. So what we have is a half the base, which I'm going to do the green triangle first. The base is 30 times OR, plus GS, we actually worked that out earlier on. We should have that as 54.4. So this is going to be a half, this is the yellow triangle, 54.4 times OR. All the perpendicular heights are OR. Plus a half 58 by OR, so that's the triangle we've done in part I, which is just 29 OR. So when you work those out, we get the first one half 30 OR, that gives us 15 OR, plus 27.2 OR, plus 29 OR, and adding those together gives us 71.2 OR meters squared, which is exactly what they wanted. So it's breaking that big triangle into three little triangles, and that part I was kind of leading you how we could do that. So now it asks us to find the value of OR. So what we've done in part C is we found the area of triangle SGH, and we said that that was 806.65 meters squared. We also then in part DII, so D part 2, worked out SGH in terms of OR, and we said that that was 71.2 or meters squared. So therefore we have a little equation that says, well, 806.65 must equal 71.2 or. Therefore or must equal 806.65 divided by 71.2, and when we work that out, we work that as 11.3 meters. So part E is then a 3D trigonometry question. Notice that our triangle SGH is at the base here. So it's at the bottom, we can still see that. It tells us that ST is a vertical pole and the angle of elevation is 14 degrees. So there's a 14 degrees that we want to put in here. And they want us to find the height of the pole and give your answer in meters correct to one decimal place. So I'm just pulling in the triangle that we have here. We also knew that that was 54.4 meters. We are looking for this ST, and all we know is the angle of elevation. However, the side PS here, we should be able to work out going back to our triangle at the start of the question. So looking at this line here. Now there's two different ways that we can approach this. Personally, I prefer to work with just right angle triangles when we can. So that's the way I'm going to focus. So we know that that OR is 11.3. And I actually know what this angle is. Because that is the incircle, the way we create the incircle is by bisecting the angle. So the full angle was 30.75 degrees. And if we bisect it, we're going to divide it in two. That will mean that this angle is 0.375. So 0.375 degrees, which basically gives us a triangle that I'm going to sketch out here. So there's 15.375 degrees. There's my right angle triangle. There's 11.3, and this is the red side that I want. Okay. So it doesn't really matter what we call it. I'm going to call this X. Think about our labeling. This is my hypotenuse and this is my opposite. Working with right angle triangles, I'm going to have the sine of angle A is opposite over hypotenuse. And that gives me a little formula that is the sine of 15.375 degrees equals 11.3 over X. Rearranging that is 11.3 divided by sine of 15.375 degrees, and that gives us X equals 42.619 meters. That is the length of PS. Is 42.619 meters. So now I go back to my diagram here and I 42.619 meters. So I have another right angle triangle that I can work with. And in this right angle triangle, I'm going to keep my color coding that I have. So you can kind of see that red line the whole way through. Love a bit of color coding. I think it keeps you very clear in the question. 619. This is what we're looking for. I'm going to call it Y because we've already used X, and this is 14 degrees. Labeling, this is my opposite, this is my adjacent. That means I'm talking about tan of the angle is equal to opposite over adjacent. That is the tan of 14 degrees is equal to Y over 42.619. Y is equal to 42.619 times tan of 14 degrees. and that gives us correct to 1 decimal place, y equals 10.6 meters, and that is actually ST. So you could have also, and I'll give you this little note, so an alternative way to deal with this, so an alternative would be to use the sine rule. So you can actually, instead of using the right angle triangle, you can use the triangle. So from down here, you could use the triangle HPS, which is non-right angled, and then we use the sine rule. If you do it that way, you get a slightly different answer. You actually get TS is equal to 10.7, and that difference is due to rounding. So if you do it that way, you'll get PS equal to 42.73, which again is slightly different, and the difference is due to rounding. And they're absolutely fine. They'll accept both answers due to rounding. They told you to do the rounding earlier on the question, so they cannot penalise you. So the rounding is actually our answer, the main one, 10.6 is the least accurate because we've used that angle to 30.75, which was rounded. So if you do it an alternative way using the sine rule, well then you'll get a slightly different answer, and that's fine. But I would always say, like with these 3D trigonometry questions, you should be able to use your right angle triangles, and use your right angle triangles. Unless you really like the sine rule and cosine rule, I would be doing the more basic formulas where you can. Example 3.2, 3D trigonometry. Find the cosine of the acute angle between the two diagonals of a cube. So this is an interesting question, and I would spend a little bit of time really focusing on the fact that they talked about the cosine of an acute angle between two diagonals of a cube. They didn't give us any information about the cube, so the go-to would be to say, well, let the side equal x. However, if they said that and we were going to get a different answer, they would have to tell you the length of the side in terms of a variable, and they'd also have to say the cosine in terms of that letter. It's too open for you to put your own variable there for the length of the side. In this case, then, what we would think is, well, does it actually matter? And the answer is no, because when we have cubes, they will be congruent. When we have cubes, they will be similar. So when we make them bigger or smaller, they still remain the same shape, they just change sizes. That means that the angles will stay the same. So the angles in there will not be dependent on the length of the sides. So what that means is, yeah, you can use x for the length of the side, but actually it will be much nicer for us to just be able to put any value we want in to be the side of the cube. So what we're going to do is let cube be of side, depends what you like, I would say literally like 1 meter. So then that is 1, 1, 1, etc. Because it does not matter. And the first place I'll always look is on the base. So I'm going to look down on this cube, and I'm going to try get this diagonal here in red. So what I have is, I have this square base, and that's 1, 1, 1, and 1. And then I have this diagonal here. And I'm going to work out the diagonal of the base. So to do that, I use a right angled triangle that has 1, 1, and I'm trying to work out that side. So that's CAB when we're talking Pythagoras, and we get c squared equals a squared plus b squared. So c squared equals 1 squared plus 1 squared. So c squared equals 2. So c is equal to root 2. So the length of that diagonal is root 2. So going into our diagram, we've just worked out that that is root 2. I'm now going to look at different triangle. I'm going to do it in yellow. That goes up along the diagonal, down the side, and across. And I'll know that this is 1 because it's a cube. I know the base is the diagonal we just worked out, which is root 2, and I'm going to work out the long diagonal. The reason we're going to work out that long diagonal is because we know that actually the diagonals of a cube bisect each other. So these will all be of the same length. So if I can work out that yellow diagonal, then we'll be able to have it to work with the triangle that will be helpful. So this is the diagonal of the cube. So last time was the diagonal of the base. We're now going to talk about the diagonal of the cube. So we have the triangle we want to work with, and that triangle is again a right angle triangle. This is the great thing about 3D trigonometry. 90% of the time you're working with right angle triangles. So you have root 2, and we want to work out this side here. So this is CAB. C squared equals A squared plus B squared. So we get C squared equals 1 squared plus root 2 squared. So C squared is equal to 3. So C is equal to the square root of 3. So that comes here, root 3. And that is the whole diagonal across there. So now what I'm going to focus on is this triangle here that has the angle that we want to work with. Okay, so that triangle here. So we're going to pull out that triangle, and I'm going to turn it what I would consider like right way up, considering this is the angle we want. That means that this side is equal to this side, and this side is 1. Both of these sides are half the diagonal, so it's going to be root 3 over 2, and this one is again root 3 over 2. And we're trying to find that angle. It is not a right angle triangle. I did say 90% of the time. It's not a right angle triangle. So we're actually going to use our cosine rule. So our cosine rule means that this is the angle we want. We'll call that A, and then we'll call this B, and that's side B, and this is C, and this is side C. Our cosine rule is A squared equals B squared plus C squared minus 2BC cos of A. Filling in, we get 1 squared equals root 3 over 2 squared plus root 3 over 2 squared minus 2 times root 3 over 2 times root 3 over 2 times cos of angle A. Not great, but we just need to do a little bit of work there. So I'm going to move over here and do a little bit of cleanup. That's 1 is equal to 3 over 4 plus 3 over 4 minus 3 by 3 gives us 3 over 2 cos of A. Just some things. That minus 3 over 2 is in front of that cos of A. Sometimes students leave a big gap there and then they add things and it all becomes a little bit messy, but be really careful. That's effectively the coefficient. So what we get is we can only add this and this. The other one is like a number in front of the x. It's a coefficient. It can't be added. So when we add 3 over 4 and 3 over 4, we get 6 over 4, which is 3 over 2 minus 3 over 2 cos of A. Bringing that across, we get 1 minus 3 over 2 equals minus 3 over 2 cos of A. So that's minus a half equals minus 3 over 2 cos of A. Breaking that down, we get 1 is equal to 3 cos of A. So what did I do there? I multiply both sides by minus 2. And multiply by minus, so sometimes it looks a bit xy. So minus 2. And again over here by minus 2. And the last step is to get cos of A on its own, which is going to be a third. Now you don't need to work out A because the question asks for the cosine, so that is a third. So there's quite a lot in that question. It was part of the question. It wasn't the whole 25 marks, but there was a good bit and there was very little guidance. That's the 2019 question, but it wasn't a difficult question. I think if you could spot that it didn't matter what length the side of the cube was, instead of having x's, it made your life a lot easier. If you left in x's, it would still work and they would all cancel out in the end, but it's very hard to work with them as well as angles and trigonometry. So example 3.3, using our identities, show that the cos of 2 theta is equal to 1 minus 2 sine squared theta. So we're going to use some double angle formulas here. Cos of 2 theta. So we have a few here to choose from. We have this one here. We also have this one with tans, but that's probably not going to be very helpful. So we're going to actually say no, that one's not going to be helpful. There are actually two more. There's this one here and this one here. Now, would you put in the one with cos squared? No, because that would make no sense. And could you use this one? Well, this is actually the one we're trying to prove, believe it or not. When you rearrange that, multiply both sides by 2, so you get 2 sine squared A is equal to 1 minus cos of 2a, and then we get cos of 2a is equal to 1 minus 2 sine squared a. So we can't use that because that's the one we're trying to prove. So we're actually left with then just one we can use. So we have the cos of 2 theta is going to be equal to, based off this formula here, cos squared theta minus sine squared theta. Okay, so I definitely don't want a cos squared theta, so I need something that might get rid of that. And we have a really useful little formula from page 13, and that is that cos squared A plus sine squared A equals 1. This can also be rearranged in whatever way we want. So in this case, cos squared A can be written as 1 minus sine squared A. So putting that in, 1 minus sine squared theta minus sine squared theta, and cleaning that up, we get 1, I have minus sine squared theta minus sine squared theta, that's minus 2 sine squared theta, which is exactly what we want. So let's fill in that cos of 2 theta, cos of 2 theta, that's exactly what we want, QED. So part B of that question, let cos of A equals y over 2, where A is between 0 and 90 degrees. That means it's acute, and that means we're only dealing with positive answers. So think of your unit circle, everything is acute. Write sine of 2A in terms of y. First thing I want to do is see, well, sine of 2A, can I break it down? And we can. There's two different formula we can use. We can use this one, or we can use this one. Now we don't have tan, but we could work it out. However, I don't particularly want to work with this fraction one, it's a little bit too difficult, so we're going to work with that sine of 2a equals 2 sine a over cos a. So this is the one we're going to use. So before I can work with that, so sine of 2a is equal to 2 sine of a cos of a. So we know the cos of a, but I want to work out the sine of a. So before I do that, I'm going to go to my right angle triangle and I'm going to say, well, cos of a is y over 2. So the formula for cos is adjacent over hypotenuse. This is my hypotenuse, this is my adjacent, and this is my opposite. I want to work out sine of a, and the formula for sine of a is opposite over hypotenuse. So I'm going to use this little right angle triangle to figure out my opposite. So my hypotenuse is 2, my adjacent is y, and I want to figure out my opposite. So I'm going to label it for Pythagoras. There's CAB. C squared equals a squared plus b squared. So 2, oh, wanted to change my color there, it just didn't want to change. 2 squared is equal to y squared plus b squared. B squared is equal to 4 minus y squared, and that gives me b is equal to the square root of 4 minus y squared. So this is square root of 4 minus y squared, and that's my opposite. So sine is the square root of 4 minus y squared all over the hypotenuse, which is 2. So going back over here, sine of 2a is equal to 2 times sine of a, which is the square root of 4 minus y squared all over 2, times cos of a, which we already knew was y over 2. We get a little bit of cancelling happening, but nothing major, and we get y square root of 4 minus y squared all over 2. And that's your final answer for sine of 2a. It cannot be simplified anymore. Be careful, sometimes students start cancelling those square roots with the fact that 4 is squared and y is squared. But if you were to factorise that, that would be a difference of 2 squares. So those two brackets would not be the same. Example 3.4, solving equations. So find all the values of x for which sine of 3x is equal to root 3 over 2, where x is between 0 and 360 degrees, and it does say x is in degrees. So the first thing I'm going to do, and I would strongly suggest that you do, is to change that 3x. So I'm going to let 3x equals theta. And the reason I strongly suggest that students do this is because it is too easy to divide by 3 too early in the question. And if you're dividing by 3 too early, the whole question will end up wrong. So I think by doing that substitution, the division will naturally then come at the very, very end. So if I talk about sine of theta, sine is positive. So if we go to our unit circle, there's cos is positive, all is positive, sine is positive, and tan is positive. We're dealing with the scenario that sine is positive, so we're dealing in this quadrant and in this quadrant. So we need to figure out what are those angles. So if I put an angle there and also an angle here, if I do that, these little angles, let's call them A, should match. So that A is called my reference angle. It's not as important to do it here because we're already dealing with a positive. We're already dealing in quadrant 1. But I do like dealing with this reference angle. It just means as we do harder questions, it's a natural addition to the question. So we're going to do sine inverse of root 3 over 2. I would strongly advise as well to have page 13 of the log tables open and to utilize that more so than your calculator. We're dealing with degrees, so when we get this, that is 60 degrees. So in my diagram, I have a 60 degrees here and 60 degrees here. So that allows us to calculate two different angles. So the first angle that we're going to take is in quadrant 1. And in quadrant 1, it's very easy. Theta is just equal to the reference angle, so that's equal to 60 degrees. In the second quadrant, to work out theta, it's going to be 180 degrees minus my reference angle, which is A. That is 180 degrees minus 60, which gives us 120 degrees. So that gives us the base for our two angles. Well, that gives us the base for our question. We have two angles here. I'm going to just set this up. So this is quadrant 1 and we have theta equals 60 degrees. I like setting it up in columns. And then quadrant 2 and we have theta is equal to 120 degrees. We have 3x, and what that means is there's going to be 3 by 2, which is 6 solutions. So normally if I just had an x, there would be two solutions. So every time I put a coefficient in front of that x, we are basically multiplying to get the number of solutions. So I need 6 different answers. So how do we progress from having this theta 60 and theta equals 120, so these two answers, to getting 6 different answers? So what we're going to do is we're actually going to use some rotations. So when I rotate, I'll get back to the same angle, so the value will be the same. So the first one I'm going to do is 60 plus a rotation, which is 360, and that will give us 420. Here we have 120 degrees plus a rotation, which is 360. And when we do that, we get 480 degrees for theta. Then we can do a second rotation. So that's going to be 60 degrees plus 2 rotations. I'm going to write it like this. You'll see why in the next question. But if you don't write it like that, that's not an issue. And then we have theta is equal to 120 plus 2 times 360, which will give us a theta of a 40 degrees. And you'd say, well, actually, these answers are not between 0 and 360, like we were asked, and that is true, they're not. But also bear in mind that we weren't asked anything about theta. We were actually asked about x. So we're going back to our substitution we did here at the start, that 3x equals theta. So actually, if theta equals 60 degrees, x actually just equals 20. If theta equals 420, x equals 140. If theta equals 120, x equals 40 degrees. If theta equals 480, x equals 160 degrees. If theta equals 720, x equals 260 degrees. And if theta equals 840, x equals 280 degrees. And that gives us our 6 solutions for x between 0 and 360. So it's really important that that rotation is done before the division, which is why I would strongly suggest doing a sort of substitution. And that substitution will kind of stop you doing the division too early. So there are our answers. Part B is slightly different because it asks us a few different things. It says the first thing, find the general solution. Actually find general solutions that satisfy this equation. And then number 2, hence solve. So we're going to use this general solution. So we didn't have to use that in the last go because they didn't specifically tell us to. So let's take a look. So we have 2 cos of 3 theta equals minus 1. So dividing across by 2 gives us cos of 3 theta is equal to minus a half. So that's the first thing that kind of went wrong for students. Then we're going to let, I can't use theta here, so I'm going to let 3 theta equal x. I kind of go between x and theta. So if the question gives me x, I use theta. If the question gives me theta, I use x. So we have the cos of x equals negative a half. So let's go to our unit circle. So we have C, A, S, and T. That is cos is positive, all is positive, tan is positive, sine is positive. So we want, well, where is cos negative? So cos is going to be positive in the first quadrant, negative in the second quadrant, negative in the third quadrant, and positive in the fourth quadrant. So we're going to just sketch this out. So we have angles here. This little angle, let's call it A, will match this one here, where A is the reference angle. Reference angle is the acute angle. In order to work out the reference angle, we simply take the positive answer to what we have. So we're going to take a half, and that will get us the reference angle. So A is equal to cos inverse of a half, and we work out our angle then in that case. Be careful, we are in this case, I know there's a degree symbol there, it shouldn't be there, that's a typo, it's a mock question. We're dealing in radians. So when we work out A, it's pi over 60. pi over 3, which is 60 degrees. Often students really struggle with this, so what I would suggest to help is you can actually write the degrees in beside it. Sorry, so we've lost part of that. So pi over 3, and that is 60 degrees. So that is our actual reference angle. So we need to work out what are the angles we are talking about. So the two angles we're talking about are in quadrants. This is quadrant 4, quadrant 1, quadrant 2, and quadrant 3. So we're talking about quadrant 2, and we're talking about quadrant 3. So for quadrant 2, we would usually do it, and you can do it in, I do it in a different color. So we would say, well, to figure out x, it would be 180 degrees minus a. So what does that mean for working in radians? Well, x is going to be 180 degrees, which is pi, minus pi over 3. So x then gives us 2 pi over 3. Over here, to get quadrant 3, x would actually be 180 degrees plus a. That means x will be pi plus pi over 3, which is 4 pi over 3. And there are two answers, but we can then get as many answers as we want. We're not trying to solve this straight away. We're actually trying to get the general solution. So in order to get the general solution, we're going to put in any number of rotations. Now, that means that what we're going to do is say x is actually equal to 2 pi over 3 plus some number of rotation. Now, usually it's 360, but we have 2 pi because we're dealing in radians, so it's 2n pi. So that's some number of rotation, where n is the number of rotations. And here is 4 pi over 3 plus 2n pi. Now, the question did not give us x, they actually gave us theta, so we're going to have 3 theta is equal to this, 2 pi over 3 plus 2n pi. And that gives us theta is 2 pi over 9 plus 2n pi over 3. Working exactly the same way here, we get 4 pi over 3 plus 2n pi. So theta is equal to 4 pi over 9 plus 2n pi over 3. And these are our general solutions. So this is the answer to the first part. These are our general solutions. Now, if they don't ask you, you can still always do that. We are then able to use these to get our answers. So how do we use these to get our answers? Well, we now have any number of rotations, so we're going to do first when n equals 0, when there are no rotations. We're then going to do n equals 1, and then n equals 2. The reason we're going to do these three is because, again, we're talking about 3 theta. That means there's 6 solutions. I have 2 solutions already, so I have the first 2 solutions when n is 0, 2 more solutions when n is 1, and 2 more solutions when n is 2. So I go along and I sub in n is 0, and that just gives me 2 pi over 9, and theta is 4 pi over 9. Then when we come along to do n equals 1, you can put that straight into the calculator and we get 8 pi over 9, and theta is 10 pi over 9. And for 2, theta is equal to 14 pi over 9, and theta is equal to 16 pi over 9, and we have all of our answers. So a lot going on in that question. The fact we had to first divide by 2, that was difficult. Then the fact we had to work with the general solution. Then the fact that it was in radians, all these things, but it was a mock question, so that's probably as hard as these questions can possibly get. So example 3.5, so it's a problem-solving trigonometry question. So that means it's from a section B. So there's quite a lot going on in these. It's quite a long question, and we're asked to do many different things within the one question. So in engineering, a crank and slider mechanism can be used to change a circular motion into motion back and forth in a straight line. In the diagrams below, the crank, OD, rotates about a fixed point O. The point C slides back and forth along a horizontal line, and CD is the rod that connects C to the crank. The diagram below shows three possible positions for C and D. OD is 10, so that's the actual crank piece, that won't change, and DC, the connecting rod, is 30 centimeters. That won't change. So what will change is that length from C to the edge of the circle. Okay, so there's our three diagrams. Let's see what they're going to ask us. The diagram below shows a particular position of the mechanism where DOC is 15 degrees, that's given on the diagram, and find COD correct to the nearest degree. So they're asking us to find this. We don't have a right angle triangle, so what we're going to do is we're going to use either the cosine rule or the sine rule. Because we have two angles, or because we have an angle and we're looking for the other angle, it will be the sine rule. So this side here is already C, or this angle there is already C, so I'm going to call that side C. I'm going to call this B and this angle B. So our formula would be usually B over sine of B equals C over sine of C, but we've already spoke about the fact that actually the reciprocals work as well. So I'm going to do it as sine B, which is what we want, over B is equal to sine C over C. So what we get is the sine of angle B, that's what we're looking for, over 30 is equal to the sine of 15 over 10. That means the sine of B is equal to, multiply both sides by 30, and we get 3 times sine of 15. That means B is equal to sine inverse of 3 sine of 15. Just double check that your calculator is back in degree mode if you changed it to radian mode for previous examples. And when you work that out, we're going to get B is equal to, correct the nearest degree, about 51 degrees. So that means angle D, it says angle COD, so they asked us, is equal to 51 degrees. So part B, as D moves in a circle around O, the angle alpha, which we worked out for one position, increases. The distance CX can be considered to be a function of alpha and written as f of alpha. If that is the case, write down the period and the range of the function. So the period is how long until it does a full rotation. So that's going to be 360 degrees, or if you prefer radians, it will be 2 pi. There's no specification of radians, however they did accept 2 pi. But realistically, the question is in degrees, I wouldn't be using radians. So then the range. So the range is the function itself. So that is the distance Cx. So look at that distance Cx, C to the end of the circle. So the longest it will be is where it is D is at X and it's the full rod. So the biggest is going to be 30, are we in centimeters here? We are, so it'll be about 30 centimeters. So that's the maximum. So that's the top of the range. And the minimum will appear when D comes all the way over here. So when D is here, the rod has a radius of 10 here and another radius of 10 here, which will mean C will be somewhere here. and that will be another 10. So the minimum value will be 10. So when it is complete the table below, give your answer correct to 2 decimal places where appropriate. So 0 degrees is 30. When it's 180, it's going to be 10. When it's back to 360, it's going to be 30. So the two that we need to focus on is 90 degrees and 270. So let's look at that scenario there. So I'm going to just rub out everything we had on my diagram here. And we're going to say, well, let's imagine that we move this, we move the crank so that it goes straight up. So we have 90 degrees, and then C comes up somewhere like this, and we're trying to find D comes up to here, and we're trying to find CX. So what we have here is a right angle triangle. And in the right angle triangle, this is 10. That's D, that's O, and that's C. And this doesn't change, that's 30. So we want to work out CO. So we're going to use Pythagoras. So there's CAB. So we're going to have C squared equals A squared plus B squared. And working that out, we get 30 squared equals 10 squared plus b squared. So b squared is equal to 900 minus 100, which is 800. So b is equal to the square root of 800, which is about 28.28. So that's b. So that's that length here. So we work out this piece is about 28.28. However, you only want C to X, so you actually only want this piece here. Now we know that this is 10 because that's standard. That means, so therefore, the length of C to X in this scenario is going to be the length from C to O minus 10, which is 28.28 minus 10, which is 18.28. And that will be the same for both scenarios, because when we come to 270 degrees, all that's going to happen is that that triangle is going to flip. So it's going to come down here. So let me try into a different color. We're going to come down like this, and the crank is going to come like this, and we have the same triangle. So use your values from the table to draw a rough sketch of f in the domain 0. So alpha is between 0 and 360 degrees. So we're going to get something like this. Straight away, you should be able to see which trigonometric function are we dealing with. In order to figure out which trigonometric function we're dealing with, we need to first look at the midline. So adding in that midline here, so it goes between 10 and 30, so the midline will be at 20. We can see that the function starts above the midline. So the sine function will always start at the midline, while the cos function will either start above it or below it if it's a negative cos. So this means what we're dealing with is a cos function. So we have cos. It is rotating in 360, so that's okay. So it's just cos of alpha, but it does go up and down, which means we're going to have to take into account the amplitude, which is this height here, and that is the number in front of cos, and then we have to add to it how far up the midline has moved. So the midline should usually be at 0. So that means we're going up to 20 as well. So actually, I think I've made a mistake here on that amplitude. I think the amplitude, should actually be 10. So that's the height between 20 and 30. So this is our function. Now, they didn't ask us to do that, but it can be useful to understand that. That is a question we see quite a bit. So being able to make this function very quickly from your graph is a really good skill to have. So the next part, I've just put the diagrams from the start of the question because they're going to talk about that here. Referring to diagram 1, 2, and 3 near the start of the questions, these ones above, for which of the three positions of the mechanism will a 1 degree change in alpha cause the greatest change in position of C? So what we're talking about is, with regards this function, we're looking where is there a biggest change given a degree change. So we're looking in the function in your graph, where will one move along the x-axis have the biggest impact on the y-axis? And what we're talking about there is slope. So where is there a biggest slope? Now we have here the max position, and that means slope is 0. We have then two scenarios here, 2 and 3. So where will there be, I suppose, the biggest change? So do we have where there is a little acute angle, or here we have quite a big obtuse angle? What I would say is, if we look at this, this angle here to me is smaller than this angle here. So that means what we're dealing with is the movement after 180 degrees in diagram 3 is less than the movement from 0. So we're closer to 180 degrees in diagram 2. So if we go and look at the graph, what we'll find is, oh, where is the graph steepest? And I would say diagram 2. I think if we actually look at that graph, so diagram 2. So from graph, we would say that that has the biggest slope. So it will be steepest. So we're talking about the slope is biggest at that point. Now you could argue into 3, but I do think 2 just has it pipped slightly. So you should be able to see that from your graph. The diagram below shows another crank and slider mechanism with different dimensions. In the diagram, AB is equal to 36 centimeters, that's given on the diagram. The length of AX is 31 centimeters, again given on the diagram. And angle BAO is 10 degrees, again given on the diagram. It tells us that angle OBA does not equal 90 degrees. So find or the length of the crank. So the only thing that's not given on this diagram is the fact that this is also or. So this whole length is going to be 31 plus or. We have a non-right angle triangle, so we're going to use the cosine rule. A is already labelled here, so I'm going to leave that there and call this side A. B is already labelled here, so I'm going to call this B, and I'm going to call this angle C. In our diagram, so we're going to sub in from our diagram into our cosine rule. So we end up with or squared is equal to 31 plus or squared plus 36 squared minus 2 31 plus or times 36 times cos of 10 degrees. So not particularly nice, but we're going to work through it, and we're going to work through this algebra. So squaring this, we have or squared plus 62 or plus 31 squared is 961. 36 squared is 1296. Then I'm going to do a little bit of cleanup here. So I have minus 72. So what I'm focusing on is the minus 2 by the 36. Remember, multiplication is commutative, which means we can do it in any order. 31 plus or times cos of 10. I'm going to do or squared minus or squared here. I then have a 62 or. I'm going to add, so this was kind of brought over that way. I'm going to add these two bits together. So 961 plus 1296. And we get plus 2257. Bit of multiplication, 72 by 31 is minus 2232 cos of 10 degrees minus 72 or cos of 10 degrees. So we end up with a 0 here. I'm going to focus on things that, let's see if I get my highlighter, ors, that have ors, and things that do not have ors, so the green. Much easier to work with the things that do not have ors, so I'm going to put that straight into my calculator. 2257 minus 2232 cos of 10. Make sure your calculator is in degree mode. And when we do that, we get 58.9. Now, for the yellow piece, okay, so we're going to work a little bit with the yellow piece over here. And I'm going to show you a way we can work with it. If you put into your calculator 62 minus 72 cos of 10, so completely ignore the ors. Put that into your calculator, 62 minus 72 cos of 10. When you get your answer, which is minus 8.906, all you have to do is put an or then at the end of it. So as long as you remember to put the or at the end of it, you can just stick that into the calculator like you would any other number. So that's our little calculator piece there. So what we actually get is minus 8.906 or. So bringing that across the equals, 8.906 or equals 58.9. And working that out, or is equal to 58.9 divided by 8.906. And that works out about 6.62, but they want this correct to the nearest centimetre. So that means, therefore, or is equal to 7 centimeters. So understanding how to use the calculator to your advantage is fantastic, and I would definitely suggest in trying to get used to doing that, especially when we've complicated pieces of algebra, that if it has something you don't want to put into the calculator, we do the same thing with pies. Put in all the numbers and then just add that letter at the end, and it's absolutely perfect. Example 3.6. So this example is focusing on a trigonometric function. Although trigonometry is traditionally a paper 2 topic, we do see trigonometric functions primarily on paper 1. Now, they have appeared on paper 2, but I would definitely be ready and not be surprised if you see one on paper 1. So the depth of the water in meters at a certain point in a harbour varies with the tide and can be modelled by a function of this form. So this is our function. So they've told us it's a cosine function. So it's a cosine function with three extra pieces. So the normal cos function is a cos of an angle, so cos x or cos t, and it will have a maximum of 1, a minimum of -1, and it will rotate, it will do one full rotation in 360 degrees, or 2 pi radians, because this question is in radians. We have some extra pieces here that we'll need to focus on. So there's an A, a B, and a C. So that will impact on how the function looks and the values. So they tell us T is the time in hours, so that's important, from the first high tide. A and B and C are constants, and CT is expressed in radians. This question is all radians. On this Saturday, the following is noted. The depth in the water at high tide is 5.5 metres, low tide is 1.7 metres, and high tide started at 2 a.m. and 14:34. So what we have is the number of hours from first tide to tide. So this is actually T equals 0. And this one here is T equals 12 hours 34 minutes, which you have to then be able to convert into hours. To do that, you can write it as 34 over 60. And then that will give you, in decimal, 12.4 5, 6, 7 hours. So just be careful the difference between minutes and decimals when we're talking here with time. And it says use the information you are given to add as accurately as you can labeled and scaled axes to the diagram below to show the graph of F over a portion of that Saturday. The point P should represent the depth of the water in the harbour at high tide on the Saturday morning. So putting in my graph, we get something like this. So the x-axis represents, let's write this in, time in hours since first high tide, which happened at 2 a.m. and high tide. And I've given there that we are talking about t equals 0 is 2 a.m. We were also given a maximum and minimum, so that point P is at 5.5, and we were able to make an axis based off that. The x-axis broken up into hours was based off the fact that we know that this point here is the second high tide, so it should be at around 2:34, which is about 12 and a half-ish hours after the first high tide, which ties into what we have here. So it was nice in the sense that the boxes were pretty standard. So 2 boxes represented 1 meter on the y-axis and 1 box represented 1 hour on the x-axis. So the next thing that I would suggest that you put into the diagram, I'm just going to take out my point has slightly moved here, is a midway line. Now, the midway line, if we're talking about a normal function, and when I say a normal function, I mean sine or cos that has no transformations. So it's sine of x, cos of x. Our midway line is always our x-axis. It's only then when there is a transformation do we see that midway line changing. That's going to become really, really important, and it's something that I suggest that as soon as you sketch or you draw a function as part of these questions that you enter that midway line. Now, how do we know where to put the midway line? So it's not just as simple as eyeballing it and think, yeah, that looks about right. The midway line, based on its name, is midway between the highest point and the lowest point. So what we have is a high point of 5.5 and a low point of 1.7. So if we add 5.5 and 1.7, and we get 7.2, we then divide that by 2 to get 3.6. So it's like an averaging. And that will actually give us exactly where the midway line needs to be, which is 3.6. So we can see it drawn in there. In this question as well, they kind of started and ended the graph at the midway point, but midway line, but we can't say for sure that that will always be the case. So the next thing they ask is find the value of A and the value of B. So these were 2 different constants that appeared in the original function. So the function was f of t is equal to A plus B cos ct. Now, this will always be true for any function. That A value, that constant that is simply added to either a sine or a cos function, that is going to shift the y values up or down. If it's positive, they'll shift up. If they're negative, it'll shift down. Basically, for our functions, that will always be how far has the midway line shifted up. So, or down, in this case it has been moved up. So it's usually the x-axis and we're asking how far has it been shifted up. If we had no A there and it was just B cos ct, that B would represent the range. So if it was 3 cos, we would know the range would be minus 3, 3. But that's only because the x-axis is the center line. There's like a symmetry there above and below the x-axis. Once we have a shift, that's no longer true. So instead we can think of it as the amplitude or the height of each of the waves. So here's my graph again. I'll go through the letters and see if we can figure this out. A, how far is the midline being shifted up? Well, it should be the x-axis, which is here, and we're shifting it up like this. So I have added 3.6 to move it up. So that gives me my value for A. A equals 3.6. At B, the coefficient of cos is the amplitude or the height of the wave. So that's basically the distance between the midway line and the maximum height, or the midway line and the minimum height. For us, that's 1.9 meters. So you can work that out between 5.5 and 3.6, but that will give us the number in front of our sine, or in this case, our cos. So B is 1.9. These things tend to stump students a little bit, but once you have an understanding of where these come from, it actually isn't that difficult. A lot of this is just simply pulled from the graph. So part 2, show that C is equal to 0.5 correct to 1 decimal place. So again, here is my graph. Remember that we are now dealing with the function f of t equals 3.6 plus 1.9 cos of ct. And we're trying to figure out that c. That c is in front of the t and it's part of the angle. So we've already talked about how putting a number in front of the angle will change the graph and how it affects the period. And from previous videos, if you've watched them or your own knowledge, you should know that the period is always given as 2 pi divided by the number that's in front of the angle. So in this case, it is a c. The letter I would generally use while we're teaching it is n. So that's how I'd figure out the period. Now, in this question, we know the period. We know how long it takes to get to high tide again. I've marked that in on my graph in red. It's 12 hours 34 minutes. Remember, that was 2:34, which is 12 hours 34 minutes after the first high tide. So rearranging this formula gives us, well, C, the letter we want, is 2 pi divided by the period. So that formula is a really useful little formula to be able to work with. Working with the period, it's important that it's not broken into hours and minutes like we have there. So instead, we're going to change that to hours. So it's 12 hours and then 34 over 60 minutes. Well, 34 minutes, which becomes 34 over 60 of an hour, and then we're able to work out that's 12.567. So into our formula, you get 2 pi over 12.567. And working that out, it gives you 0.499999, which is approximately equal to 0.5 as requested. So really important formula to know. This one can get you out of a lot of trouble very quickly. So this question can be done in another way using the function, but it's much longer. So if you can remember that formula, it'll be great. So the final part is use the equation f of t is equal to a plus b cos of ct to find the times on the Saturday afternoon when the depth of the water is exactly 5.2 meters. Give your answer correct to the nearest minute. So going back to my graph, I'm looking and saying, well, where's 5.2? And I've added in a line to see where roughly it cuts the axis. So it asks us to use the equation, not the graph, but I'm using the graph to give me a little bit of guidance. So here I can see I have 3 specific points. The first point is here, and that is roughly about an hour after 2 a.m., so by 3 a.m. That is not in the afternoon. So we have to be very careful. That is not in the afternoon. The second point is here, which is kind of about 11 hours after 2 a.m. And that's okay. So that's about 3 o'clock in the afternoon. And then this one here seems to be just before, where are we? So it's about 13, 14, just before 14 hours. So again, we're talking about 4 o'clock in the afternoon, maybe 3 something. So the 2 points I want are actually the second 2 points. So we're going to work with 3 specific points. So from the graph, notice that there are 3 times where f of t is equal to 5.2 meters, and we need to work with that. One of these appears within the second rotation. Remember, I hit my first rotation here. I completed there. So this third point is into my second rotation. So I'm going to need to do a rotation. So working through that, we start with the f of t with everything filled in. So I have my a, I have my b, I have my c. I then let that all equal to 5.2 because that's what I'm trying to solve. I rearrange this, so I bring my 3.6 over and then I divide by 1.9. Just be really careful. You can't add the 3.6 and the 1.9. The reason being that 1.9 is a coefficient of cos. So it's the same thing as having a 3.6 plus 1.9x. You couldn't add it in that case. So just because it's in front of the cos, don't do anything you wouldn't do in algebra. So when we work that out, well, before I work that out, I'm actually going to let 0.5t equal theta. So I'm going to solve this like we would usually solve an equation. This is your step-by-step like you would usually do it. The reason we substitute in a theta rather than 0.5t is to avoid getting our t too early. So that's going to give me cos of theta is 1.6 over 1.9. Don't forget the question to tell us radian. So before you do anything in your calculator, double check your calculator is in radian mode. And then we do theta is equal to cos inverse of 1.6 over 1.9. And theta is equal to 0.5696. So that's one answer. And I know there's going to be 3 answers, the last 2 of which I actually want. So how do we get more than one answer? Well, we're going to use our unit circle. So the 2 places where cos is positive is quadrant 1 and quadrant 4. And they're listed here. You should be able to see the little diagram up there on the right. So the first quadrant, very straightforward, it's 0.5696. In quadrant 4, using the reference angle as 0.5696, it's usually 360 degrees minus the angle. In this case, we're doing radians, so it's going to be 2 pi minus the acute reference angle. And that gives us theta equal to 5.7136. So at this point, I only have 2 answers. So to get my third one, I go back to my first angle and I add a rotation. So here I'm going to find theta as the previous angle plus 2 pi, which works out about 6.8528. So now that I have my 3 thetas, I need to go back and get t. So the first one is if theta is equal to 0.5696, then 0.5t is equal to 0.5696, and then I can work out t, divide both sides by 0.5, and you get 1.1392. So that's 1 hour and 8 minutes after high tide, which is 3:08 a.m. That is not valid because it is not an afternoon time. The second angle we're going to work with is from quadrant 4, and 0.5t is equal to 5.7136. Dividing both sides by 0.5, you get time is equal to 11.4272. Breaking that out into hours and minutes, it's 11 hours 26 minutes. So adding that to 2 a.m., so it's 11 hours after 2 a.m., it is 13:26 or 1:26 p.m., whichever way you prefer. And the last angle that we're going to take and work out the time is theta is equal to 6.8528. So 0.5t is equal to 6.8528. So time is equal to 13.7056, which is 13 hours 42 minutes after 2 a.m., which works out about 15:42 or 3:42 p.m. correct to the nearest minute.